Now we talk a little bit about complex numbers in general. We want to talk about the trigonometry portion of the complex numbers show. When we talk about complex roots of numbers. Now to do this, we're going to set up a way to visualize complex numbers. Complex numbers are just numbers with two parts, the real parts and the imaginary part. So we're just going to draw them on a set of axes. On the horizontal axis, we'll put the real part. And on the vertical axis, we'll put the imaginary part. So a complex number is just a number with two parts. So here's how we visualize numbers with two parts, where the parts are independent of each other, not like a fraction. Complex numbers have two parts, so we visualize them on the complex plane. One axis is going to be the real axis, and the other axis is the imaginary axis. So the number -3 plus 4i will have a -3 on the real axis and a plus 4i on the imaginary axis. The number 1 plus 2i will have a 1 on the real axis and a plus 2 on the imaginary axis. We're visualizing a number with two parts, so we just make two axes and plot the two parts. Now I want to look at some stuff. The number 1 has two square roots, plus and minus 1. 1 squared is 1, -1 squared is 1. If I was to plot this on the complex plane, here's 1 and -1. All real numbers are also complex numbers, so I could write this as 1 plus 0i, and this one I can write as -1 plus 0i. So the real number 1 has two square roots. The number -1 also has two square roots. They're just not real. -1 also has two square roots, plus or minus I. I squared is -1, and negative I squared is also -1. The -1 gets squared, but I squared is still -1. So the negative part gets squared away, but I squared brings its own -1. And I is the imaginary unit. So -1 also has two square roots. And if I plot them on the complex plane, I'm here at 0 plus I and 0 minus I. The important thing here is that we have two square roots that we can plot on the complex plane. And they're on opposite sides. They're sitting on axis and they're on opposite sides of each other. They're 180 degrees apart. We want to notice that the square roots are 180 degrees apart. The square roots are 180 degrees apart. I want to skip 3 and I want to go right to 4 because it's easier to calculate. I want to think about fourth roots of 1. So what to the 4th power gives us 1? So there are two we can find right off the bat, 1 and -1. So if I take 1 to the 4th power, that's 1. And if I take -1 to the 4th power, that's also 1. So there are two fourth roots, but there are other ones if we allow complex numbers. If I take I to the 4th power, that's I times an I times an I times an I. I times I is I squared, which is -1. I times I is I squared, which is -1. -1 times -1 is +1. And if I grab a negative I to the 4th power, I get a -1 to the 4th times an I to the 4th. -1 to the 4th is 1. And I to the 4th is also 1, like we just found. So there are 4 fourth roots of 1. Plus and minus 1 and plus and minus I. If I plot them on the complex plane, here's 1 and -1, and here's I and -I. What we want to notice is that these fourth roots, the four fourth roots, are 90 degrees apart. We want to notice that the fourth roots are 90 degrees apart. The square roots, there were 2 of them. The 2 square roots are 180 degrees apart. The 2 square roots are 180 degrees apart. The 4 fourth roots are 90 degrees apart. So now I want to split the difference. Next, we want to see that the 3 cube roots are 120 degrees apart. So if I think about the complex plane, so if I think about cube roots of 1. Certainly 1, because if I take 1 cubed, we get 1. So now let's grab the complex plane. Think about the unit circle. And find 2 other complex numbers that are 120 degrees apart. I don't know why I do this so small. Apparently, I only got 2 modes, like full size and like micro. The important thing that we want to note here is I've got 120 degrees, then another 120 degrees would put us at 240. We've got some points that we're familiar with. So if we refer to our unit circle, this 60-degree reference angle, it's the cosine of 60, that's 1/2. So this point is -1/2 and positive √3/2. And then down here at the bottom is -1/2 and negative √3/2. So the other cube roots of 1 that we'll speculate about, -1/2 plus or minus I times cube roots of 3/2. If we want to find this out, we can just raise these to the 3rd power. Now, this would require we take a -1/2 plus I root 3 over 2 times another -1/2 plus I root 3 over 2 times another -1/2 plus I root 3 over 2. Or we could check in a slightly different way. I suppose we could grab a calculator. That would be the happy way to do this. And then we'll just pretend. The other way we can go about this is I can look at the solutions for x cubed plus 1 or minus 1. I'm trying to solve the equation x cubed equals 1, which is the same as solving x cubed minus 1 equals 0. And then we can remember how to factor the difference of cubes, which we all remember how to do, right? There's not a quiz on this, so you can just agree. It's like, oh, yes, yes. Of course, we remember how to factor the difference of cubes. One factor is x minus 1. The other factor is x squared plus x plus 1. Here's where we get the 0 x equals 1. Here's where we would solve by completing the square or the quadratic formula, where x is equal to -1/2 plus or minus I times a root 3 over 2. Great. Did we write a quadratic formula program? Now that we have our calculator in, oh, that's right. I forgot. I programmed this is quadratic formula by going to Lycosity. But there it is. -1/2 plus the square root of 3 over 2 times I, -1/2 minus the square root of 3 over 2 times I. And that verifies that we can indeed smell what the rock is cooking. Any questions? Comments? Slide them up. All right, that's it for today. That's it for this week. I'll see you all on Monday. Everybody have a good day, and thanks for playing.